Okay, so hello everyone. So this is the final session today. The speaker is Professor Matteo Baggioli from Jiaotong University in Shanghai. But actually, he's physically in Greece now. We are all NDU. And he's going to talk about fluids and ADS-CFT and black hole.
All right, so thanks a lot, King Young, for the introduction, and thanks a lot to all the organizers and the people involved in the organization of this event. It's always a pleasure to speak at this event. So today, yeah, I'm gonna tell you some recent results that we got regarding the far from equilibrium dynamics of fluids using holography techniques. And it work? Yes. So the talk is based on this paper that appeared recently in PRL in collaboration with Lili and Aoqian Sun. And let me start with some acknowledgement. So first of all, these are my collaborators from ITP Beijing. So probably most of you know Professor Lili. And I want especially to acknowledge his brilliant student Aoqian Sun that made most of the numerics that you will see in the next slides. And of course, a big thank again to APCTP and all the organizers for putting this event together. So let me start from something quite simple, just to have a common background of what I'm going to discuss in the next slides. And so the main object that I want to discuss is the viscosity. And so let me give you just a very quick definition of the viscosity from basically Wikipedia. And the simplest way to understand the viscosity is, of course, like the friction between the layer of the fluid. And the simplest, say, experiment or experimental setup where this can be visualized is what is called the Couette flow. So let me see if the video works. So this is basically the Couette flow. You just put a liquid between two planes and you start moving or pulling one of the two planes. And what you will feel a force, the resistance on this pulling. And this resistance is nothing else than a manifestation of the viscosity of the fluid. Now, in more like physical or mathematical term, this kind of viscosity is determined by what I call here the Newton's law of viscosity, which relate the stress and basically the gradient of the velocity in the transverse direction. So to make this picture more precise here, whenever I pull this plane, basically the velocity will not be uniform in the vertical direction. There would be a gradient. So certain layers will move faster than others. And this will create basically a transport of momentum in that direction and a resulting force or stress, which is given by the formula. So as a clear analogy, you can think about the elastic Hooke's law for springs. So the only difference is that here, the stress is not proportional to basically the deformation itself, but it's proportional to the shear rate. So it's a rate of deformation, and I need to do this in a non-dynamical way. Now, let me stop the video. So, of course, different liquids have different viscosities, and here it's just a very simple visualization of two very standard liquids. Here you have water and honey. Honey is more viscous than water, and therefore you see it shows more resistance under flowing on surfaces, etc. Okay, now going more into, let's say, the setup that we are more familiar with, which is basically Plativistic Hydrodynamics, the viscosity manifests itself as a dissipative transfer coefficient in the constitutive relation of the stress tensor. So here I wrote the generic form of the stress tensor for, say, a simple fluid. And so here you see that there is basically the equilibrium configuration, the equilibrium contributions, which are just the energy at the pressure. And then you see two terms, which are the leading dissipative term, which are first order in derivative. And one of them is the viscosity, and the second one is the bulk viscosity. And the one that we will be interested in is the shear viscosity. So importantly, you see that basically this constitutive relation here is nothing else than a manifestation of the same mathematical law that I wrote before. So if you think that the stress tensor, or at least some component of them are stressed, then this weird tensor in the bracket is nothing else than the shear strain rate. So it's basically the relativistic version and the covariant version of that object that I was writing before. So you can imagine to start, for example, with a square, and you start off shearing. So shearing is the deformation that change only the angles, but does not change the volume. And you can imagine to do that at a specific rate. And that's why here you have basically derivatives. And then basically the coefficient that tells you how much stress is created by this kind of shear rate is the viscosity. And so this is, of course, all common standard knowledge. And for those of you who are not familiar with this, I really suggest the Cofton lectures about relativistic hydrodynamics. And so why we are interested in this object? So there are many reasons why you want to be interested in the viscosity, but at least for our community, probably the biggest motivation comes from the fact that the viscosity has shows a kind of universal behavior, and in particular as a minimum, and even maybe a bound from below. So this is a famous plot that you can find in various places where there are displayed various liquids. So you can see there's water, helium, and Fermi gas, and then quark gluon plasma. And on the bottom, the dashed line is the famous Cofton Starinets bound that was discovered using black hole dynamics and holography techniques. So let me be a bit more clear about what is really the viscosity doing. So the viscosity is governing what is called shear diffusion. And so shear diffusion is basically the diffusion of transverse momentum, and the mode related to these dynamics is the one on the top right. And if the fluid is neutral and relativistic, then the diffusion constant of the shear diffusion constant, or at least the dimensionless version of the shear diffusion constant, is just the ratio of the viscosity over the entropy. And that's why people like a lot to plot basically this ratio, because in other words, this is what governs the diffusion of momentum. And of course, if one wants to be a bit provocative, one could say that actually this KSS bound was the only prediction of string theory, so we are kind of happy, and that's what it is. But what I want to point out is that also this kind of bounds for the viscosity is not a prerogative of relativistic systems, but it's actually something much more general. So here you can see a plot of the viscosity. Actually, here it's called nu. So it's called nu because in the context of non-relativistic liquid, usually the correct quantity is nu. I will say in a while what is nu and actually how it's related. You can see here on the bottom. So nu is the shear viscosity divided the mass density. And this is the equivalent in non-relativistic system of exactly the viscosity divided epsilon plus p. So basically the mass density in relativistic system substitute what is called the momentum susceptibility in relativistic system, which is just epsilon entropy, energy density plus pressure. Now, the interesting thing here is that you see this is the behavior of the viscosity for many different liquids. And you can see that all these liquids have two important features. So the first important feature is that there is a minimum. And the second important feature is that this minimum is actually quite universal. So you see that these are very different liquids, and more or less, they all have a minimum around 10 to the minus 7 in these units. And importantly, this kind of minimum can be derived by simple physical, let's say, arguments. And it was derived in this paper by Trachenko and Bratkin in 2020. So I really encourage you to have a look at that. It's a very simple, physical setup. And you reproduce very nicely this result. And here you see the final formula that they get. It's a formula which, of course, is given in terms of non-relativistic quantities, like you see the masses, etc. And you reproduce exactly like this 10 to the minus 7 that you see in many liquids. Now, a funny thing is that if you do the same kind of computation for the quark gluon plasma, and you put inside the number, you find that actually the quark gluon plasma in the same unit is not that far from the system. And you see that the stars is basically the equivalent quantity for this quark gluon plasma. And even more interestingly, you can find that not only the diffusion of momentum, so the viscosity, but also the diffusion of energy, which is the thermal diffusivity, which is this alpha here, has a very similar behavior. So here, for example, I just selected 4 liquids, and you see these curves are the viscosity and the thermal diffusivity. And you see that both curves behave very similarly, and they have both a minimum at a position which is very close to each other. And if you run again the argument of the of the original paper for the thermal diffusivity, you find that actually a leading order, the result that you get for thermal diffusivity is exactly the same that the one that you get from the viscosity. And funnily enough, you see that the real liquids are not that far from that prediction, even though if you see the details that we basically explain in the paper, of course, the considerations are very simple. So we make a lot of assumptions, but still, you see the results are quite compatible with those assumptions. And I find this quite surprising. So, well, this might be surprising, but maybe not much surprising for those of you working in these fields, because you're probably aware of this idea that diffusivity in certain regimes are highly universal, and of course, yes.
Oh, sorry, Matteo. So before proceeding further, I have a few questions in your previous slides. But all very simple questions. But by the way, so this kind of a bound is only discovered in all recently, because this eta over p may be very easy quantity to think, but nobody computed this until 2020.
So the fact that there is a minimum, it's a very well-known fact, and it actually corresponds to the fact that the system is a crossover from a liquid and a gas. So let me explain maybe a bit more. So in a liquid, the viscosity comes from the rearrangement of the molecules. And these rearrangements are like basically energy barrier jumps, and they are exponential. So the viscosity in that kind of system decreases with temperature. On the contrary, if you go on the right of that minimum, you are in a gas. So in a gas, now the system becomes very dilute. The particles are almost free, and the viscosity comes from the collision of the different particles. And you can just use kinetic theory, and you will find out that the viscosity is proportional to the mean free path. And the mean free path grows with temperature, and therefore you have this behavior. So the fact that there is a minimum is very well known, and you can actually, find out with this simple logic. But as far as I know, the fact that this minimum is actually quite universal in terms of numbers, and especially the derivation of a formula. So you see here there is a very concrete formula, which is very simple, that gives the simple value. To my understanding, was not done before 2020.
I see. Okay. And, thank you very much. So,
yes.
Yeah. And probably you already answered my question. So here, the first graph and the second, the difference between these two are just the scaling of the longitudinal axis, right? The same thing.
Yes. So I scaled the longitudinal axis and I put this star. This star here is related to the second paper that I referred here. See. Where we basically emphasize that if you take the quark-gluon plasma, that we always say is a very exotic fluid, and you put the number, you actually get a number for the minimum, which is not that far from the other fluid.
Okay, I see. So, and last question is, in the last graph, yes. So what do you mean by nu m is equal to alpha m?
Okay, so what I mean, I didn't explain it fully. So what I mean is that the viscosity at the minimum is actually equal to the thermal diffusivity at the minimum. So this is what you get from the theory. So if you run the theory, you can see this last paper with Kostya Trachenko and Kamran Benia. We derived this formula, and this formula, of course, has a lot of assumptions. But then if you see the real liquids, you see that the value at the minimum are actually not that far at all. And this for us was surprising because, as you know, I mean, thermal diffusion and momentum diffusion are two completely different mechanisms that in principle should not have anything to do with each other. And still in this system, in standard liquid, this is not anything weird. It's just argon or helium. The value at the minimum, it's very similar. And this for us was surprising. And but then when we run the computation, we find out that actually the simplest approximation gives that they are exactly the same. So it's not that weird.
Okay, thank you.
No problem. So then, going back, I mean, this is kind of fitting in the idea that diffusivities are somehow, can somehow be universal. And here, of course, there is a huge amount of literature that I don't want to touch. And I want just to emphasize that if this is true, why this is true, and where this is applied are still all open questions. And I think it's an interesting topic to try to tackle, and of course it has been attacked from various sides, and that's what it is. So today I want to kind of do a step forward and ask myself, like, how about this universality? So what is really this universality? What does it mean? And how much does it extend? So in particular, I want to focus on the shear viscosity, which is, as you know, a very simple computation from the holographic point of view. But I want to push it a bit more. So in particular, we are all familiar with computing the shear viscosity in the context of linear response. So that's all good. We know everything. We know how to compute it. We know how to derive it from bulk formulas. We know to derive it in terms of black holes quantities, etc., etc. But much less is known when you start going away from linear response. So remember that the viscosity is the coefficient between the stress and the shear rate. So here by linear response, I immediately mean the situation in which the shear rate is small. And whenever the shear rate is not small enough, of course, linear response will not apply. And then we are basically left with fewer methods to compute this viscosity. And so the question that I want to basically analyze today is what happens when I make this shear rate large. And as a tool, I will use holography because that's a very simple tool in which I can basically reach that regime. So to give you an idea of
can
why
I ask
this is actually...
quick question?
Yes.
Yeah, in the case when in the relativistic case where using ADS-CFT where this transport was computed, the shear viscosity, even though it had a lower bound or lower bound or something like eta by s is equal to 1 over 4 pi, but the thermal conductivity did not had any lower bound or anything, right? Or even the conductivity, because there was always normalization dependent things that came, and it was not very clear. But in the cases you are saying both have a lower bound.
Yes. So well, the case that I'm saying here, so for the moment here, I'm not touching any holographic model. So this is real data from real fluids. And what this is showing that in real fluid, the thermal diffusivity, be careful, not conductivity, the thermal diffusivity is bounded from below, so at a minimum. Okay, so if this minimum is universal and how much this minimum can be pushed lower in more exotic systems like strongly coupled fluid, etc., that I honestly don't know. That's a good question. So in holography, you're right, the thermal conductivity, it's a tricky object, but the thermal diffusivity or the thermal or energy diffusivity is actually quite universal. And indeed, there are a lot of discussions about bounds on energy diffusivities related also to this chaos, quantum chaos. And as far as I know, actually, the bound on the energy diffusivity in holography is the only one of which I don't know any violation, or at least I don't know any holographic model that violate a certain bound on the energy diffusivity. While, for example, on the bound on shear viscosity, there are plenty of models that violate that 1 over 4 pi, and people are still trying to understand what that means or what is the meaning of that. Yeah.
Okay. Thank you.
Thanks. So yeah, now before going on and before passing to the actual holographic computations, I want to give you more, let's say, understanding of what I really mean of this non-linear response. And I want to make like some very simple example that actually you can make in your office yourself. And so the simple example is the following. So what I want to do is I want to create basically a shear rate. So I want to deform my fluid in a certain way. And I want to increase this shear rate, and I want to compute the stress. Now, there are 3 different types of fluid in general. So there are fluids. So all the fluids, when the shear rate is small enough, you see the relation between the stress and the shear rate is linear. This is just linear response. So this is unavoidable. And this is what we call, let's say, the viscosity in the linear response. So the slope is just the viscosity if you want. But then when you go nonlinear, of course, there are different kinds of situations. So the stress can increase with respect to the linear slope, and this is what is called shear thickening or dilatant system. Or the stress could actually decrease, and this is the case of shear thinning, or the stress can remain more or less linear, and that's the case of Newtonian fluids. Now, to give you an example of all the 3, you can start from this. So system where the stress actually decreases, it's the typical one is ketchup. So if you try ketchup and you put ketchup on your burger, you will notice that the moment you start pushing a bit, it's very hard and ketchup does not flow. But if you push more and more and you apply more, actually the ketchup flows much faster than before. this is this kind of behavior. On the contrary, you can try the different system, which is very famous, and in YouTube you can find many videos, which is basically water and cornstarch. And water and cornstarch is exactly the opposite. So if the force that you're applying is kind of small, then it behaves very softly, so it's very liquid. But then if you start like bumping it very hard, it becomes basically very solid. So the viscosity grows a lot. And this is the two kind of behavior. And there is a simple experiment. For example, you can look at videos on YouTube. You can just take a bowl and put ketchup and put cornstarch plus water and throw a golf ball inside and see how different the two things behave regarding the force that you apply when you throw the ball. So if you put, for example, the ball in ketchup, static, the ball will not go down because ketchup is quite viscous. And on the contrary, in cornstarch plus water, it will just fall down. But now if you throw it very hard, in the ketchup, it will go just down completely, while in the cornstarch plus water will just stay there or basically bump out. So these are the two different behavior. So these are real things. And here I want to show you just to convince you that this is real physics that we can measure. This is liquid grease, something used in various applications. And here you can see a picture on the right, and this is the measurement. So this is the measurement of the viscosity. You see the viscosity is in red in function of the shear rate. So and in blue you see the stress. So what you see here, what you see is that when the shear rate is small, the stress grows linearly with the shear rate. So this is what we know from, let's say, standard linearized hydrodynamics. And the viscosity is constant. So the viscosity is a transport coefficient that does not depend on the shear rate. But then after a certain point, and more or less when the shear rate becomes order 1, then this is not true anymore. You will see that the nonlinear response is kicking in. The stress is not anymore linear. For example, in this case, it flattens. And the reason that it's flattened is basically the fact that the viscosity, the nonlinear viscosity, is decreasing. So this means that this material responds in a way that if you increase the shear rate, actually its viscosity is decreasing, it's becoming more fluid. And so in general, what I want to convey is that the viscosity is not a number. The viscosity is a nonlinear function of the shear rate that you are imposing. And one important thing to notice is that in this context, you see that the source or the external source that I'm actually applying is a rate. So this means that if I increase this rate, not only I'm going into the realm of nonlinear response, but I'm also going in the realm of far from equilibrium. So what I mean by equilibrium, of course, I mean that the gradients are kind of small. This is the usual assumption that we do in hydrodynamics when we do a perturbative expansion in gradients. And of course, if this ratio, for example, here, which is dimensionless, this gamma dot times tau, where tau is some, let's say, characteristic time of the system, you can imagine it like in a thermal system can be the inverse of the temperature, for example. And so you can imagine that when this ratio becomes very large, obviously any expansion in gamma dot does not make any sense anymore. And therefore, the formula that I showed you at the beginning of linearized hydrodynamics does not make sense anymore, because that is based on the fact that the gamma dot is small, so that the gradient is small. So this is also interesting because pushing this shear rate high is not only going towards nonlinear response, but is also going from physics, which is not near equilibrium, but it's actually far from equilibrium. So you can imagine, like, perturbing some little waves on the sea, like just near the flat surface, or just some big waves. This is basically the difference. And of course, we know that the small waves on the surface can be kind of described with some hydrodynamics limit, while the one on the right probably needs a completely full-time, non-linear time evolution. So summary of the question. So the question that I want to ask is, we know that, at least from holographic model, that the heat over S ratio is universal when I'm close to equilibrium. So when the shear rate that I'm applying is small. And the question I want to ask today is, what happens of this universality when I push this response out of equilibrium? So I increase the shear rate arbitrarily, and I go far away from the approximation where the shear rate is small compared to the characteristic scale of the system. Is there any question here before I dig into actually the methods and the computation itself?
So just to understand this nonlinear regime, so there no longer the derivative expansion is going to work out, right? So, but will you still be able to define shear viscosity the way you define using the hydrodynamic expansion?
The answer is no, and you will see it in a few slides how you actually have to define it. Okay. Yes. So you are totally right. You cannot define it the way I did, and you cannot use Kubo formulas. Yes. Okay. I will show you in a while exactly how that works. That's a good question. Here actually is the answer. Well, part of the answer. So in the linear response, of course, that hydrodynamic formula that I wrote is valid, and one can write basically a simple Kubo formula that comes out just from the standard procedure, which tells me that I can derive the viscosity. And here, notice from now on, I will indicate with eta 0 the viscosity in the linear response regime. And this Kubo formula comes just from the definition of that constitutive relation. And it's basically what is used all the time to compute the viscosity in the linear response regime, also from holography. So the standard computation that we do in holography, I will show you in a while, is basically based on this Kubo formula. As it was pointed out just half a minute before, of course, this definition does not make absolutely any sense if you go beyond the limit of linear response and gradient expansion, because this Kubo formula is based on the fact that constitutive relation, which is not valid anymore. So the question is what you really do when you are out of equilibrium or where the shear rate is high. And here there are various attitudes. So one attitude that was kind of used in the past was like just to forget about this problem and keep using the Kubo formula, which I'm not sure it's correct. So the attitude that we actually choose is to take the definition that actually people measuring this quantity take. And the definition is very simple. The definition is basically divided the stress that now for certain reason I call sigma. So this is when I indicate sigma is always the shear stress. So it's always the component that I'm interested in. Let's say in a relativistic language would be Txy, for example. And I divide it by the shear rate. So what you can see here is that this definition obviously reduces to the usual definition when this system is linear. So if the stress is just linear in gamma dot, then the relation is sigma equal eta gamma dot, like I explained at the beginning, and then eta is just eta 0. That is exactly the equivalent. But then when it becomes like non-linear, then what happens is that sigma itself, the stress itself, is not linear anymore in gamma dot. It becomes a non-linear function, and therefore the viscosity itself will become a non-linear function of gamma. So this is the definition that we will use, and we choose this definition because this is what is actually measured. So of course, we can discuss, maybe let's postpone this discussion at the end about the meaning of this object. So if we want still to call it shear viscosity or what happens. So for example, if you think about an hydrodynamic expansion, you will see that this viscosity will be basically an infinite collection of additional transport coefficient that comes from higher order and can be repacked in a nonlinear function this way. But for the sake of simplicity and for the sake of physics, that's exactly what we measure. We will define the viscosity in this way. And just to give you an idea, this is exactly what they do when you do an experiment. So this is basically what is called a rheometer. So rheometer is the machine that actually measures the viscosity, and it's a machine that is based on a very simple principle. So you see you have this kind of container with the fluid, and you have plates, and you can basically control the speed of the rotation of this object, and you can actually measure the torque that is produced. And the speed is converted into the shear rate and the torque into the shear stress. And you can see this is a very small machine. So this is basically a tabletop experiment that you can do even in your office. So now let's go to holography. So if we want to do this computation in holography, what we do? So first, let's stay in the linear response regime. So if we want in this staying in linear response regime, what we need to do, we need to understand how to apply a shear rate to our system and how to read the response. So the shear rate is actually very simple. So our system is now a black hole, and applying a shear rate is nothing else than applying a shear mode perturbation, which depends on time. So the simplest way to do it is basically you take your space-time, whatever it is, you add on top of this the perturbation, which is here I call GXY, which depends on time. It does not need to depend on space. And the time dependence, of course, for simplicity is choose to be like a Fourier, like just an exponential. And the frequency would be basically determining the shear rate, if you will. Now, what you have to do, well, you have to run the usual method in holography. So what you do, you find the bulk solution for this. So you will have a bulk equation for this perturbation. You find the bulk solution, then you expand the solution close to the boundary of ADS. You will find that generically this boundary expansion contains two terms. And following the dictionary, the holographic dictionary, one of the two terms is actually the source, what I call the delta JXY0, and the other one is the response. So the response is the stress. So is the stress associated to basically this source, so that this source creates. And then you use linear response. So you use linear response and you can basically compute the 2-point function of the stress, which in linear response is just basically the 1-point function divided the source. And then you apply the Kubo formula that I showed before and you get the viscosity. So here it looks like very complicated, but actually this, I guarantee this is the simplest computation that one can ever do in an holographic system. And indeed, you don't even need to do numerically, you can do it analytically with methods which are well known. Now, of course, this computation that I showed there does not make any sense if this perturbation here is not a small perturbation. So whenever this perturbation is large, you cannot assume anymore this as a perturbation on top of the background, but you actually have to consider itself as a component of the background. So if you want to compute this viscosity at the nonlinear level, what you have to do, you have to consider a situation which is a bit more complicated. And in particular, you have to modify your space-time metric in a way that this shear deformation appear in the metric itself. So here is basically the notation that we use. So don't pay too much attention of the exact form. This is not exactly, important. It's just our choice. But the important thing is that you can see that the metric itself in the background now has two important features. The first feature is that the metric now is time dependent. So you see all the function of the metric are time dependent. And the second important feature is that there is a factor in off diagonal in the spatial component. In the XY component, we put this sinh of H, and this sinh of H means that basically we are deforming the space-time metric with a shear deformation. So this metric is not anymore diagonal, but we're actually changing the angle between the X and Y direction. Now, if you do exactly the same kind of analysis that I was discussing before, you will find out that this function H and this function sigma have a certain expansion close to the boundary. And here you can see the concrete form of this expansion. And what is important is that there is a source, H0. So this is the leading term in the expansion for this function, and this is what is the source. So this corresponds to basically a source in my boundary theory, which produce a shear deformation. Okay, so this source here in the boundary defines for me a shear deformation. And this H3 here, it's related to the response. At the same time, the sigma has a certain expansion. And then we can basically, with this setup, we can compute completely the nonlinear evolution. So there is a time-dependent evolution of the systems. And of course, there are many caveats. There are many caveats because now we are far from equilibrium. So one has to be very careful of defining not only viscosity, but also thermodynamic quantity. So obviously, the validity of thermodynamics far from equilibrium is, it's a topic of discussion, and at least let's say that standard naive thermodynamics probably does not apply. And one has to be careful. And for example, here I put an example of what I mean to be careful. One example is the entropy density. So one has to be very careful to define entropy density or entropy in general. And there is increasing evidence that the entropy density actually should be extracted from the apparent horizon and not from the black hole horizon that is formed because this is an out of equilibrium system. And here I give the definition. So basically you see that the entropy now is related to the area of this apparent horizon, where UA is not the position of the black hole horizon, but it's actually the position of the apparent horizon. So this is the standard thing that people do when you do out of equilibrium, let's say, analysis in holography. And of course, as you will see, I will never talk about temperature because I don't know how to define properly temperature. There are different ideas, but we find out that basically the best was just to forget about temperature and give up on that quantities. You have a question, Kenyon?
Yes, thank you for asking. So in the previous page, you have a metric form. Is that metric form is just ansatz you want to use? Or mean,
yes. Sorry,
why
I
do you
wasn't
use
clear.
that specific Cauchy and Shinch? Why do you use that kind of form there? Just
Oh,
for
okay,
convenience?
okay. So yeah, exactly. So as I said, do not focus too much on the Cauchy and Shinch. This is just for convenience, such that the equations become simpler. In principle, the only important thing that you have to notice here is that you need an ansatz which is time dependent, and you need an ansatz which contains an off-diagonal term.
I see.
Now, notice one thing. Actually, yeah, no, this is a good question. So there is one thing. We wrote it this way because then you can see that the terms in the bracket is actually unitary determinant. So this means that H does not change the volume of the spatial slide. So you see all the volume changes in the XY plane are basically contained in the sigma. So sigma is basically determining all the deformations that relate to volume. Well, volume in this case is surface, it's just a 2D, but yeah, that would be volume. While H is responsible for every deformation that changes the angle. Yeah, that's a good question. Sorry, I forgot to say that. So
then probably at the end of the day, anyway, you will obtain D and H satisfying the Einstein equation numerically, right? At the end of the day.
Yes. Then what you have to do, which is what I will outline after, is that you have to take basically these answers and compute, well, assume a model. Now you will see which models we will assume. And then you compute the full time evolution of your system by putting a shear rate. So as you will see, this H0 here, it's basically the shear deformation. So the time derivative of this H0 will basically determine the shear rate for me.
Okay, thank you.
What I want to do, I want to solve numerically all the system, increasing the shear rate and reading the stress and then the viscosity in this setup.
Okay.
That's what I want to do. Yes. So yeah, that's actually what I was trying to end up here. So you have to do a bit of computation. These computations are kind of, let's say, standard, but not necessarily simple. And you have to do all the holographic normalization of the systems, and there are some caveats. The caveats are related to the fact that the boundary metric now is not Minkowski, so you have to be a bit careful how you define things. For example, for those of you who are not familiar and are curious, I suggest the Kenderis lecture. And then after all this computation, basically what you get is the definition of the two objects that we're interested in, which is the stress. So the stress is given by this contribution. You see, if everything is time independent, so if you remove all the dots, you will find the usual expression. So the usual expression is actually the sigma is H3, right? So this is the usual expression that the stress is the sub-bleeding of the solution. Now in this setup, which is time dependent, this is not true anymore. So you have correction that comes also from the rest. And this is what you see here on the right side. So once you have this definition of the stress, so every time you solve numerically, basically your system, then you know numerically what are H3, H0, S1, S2, etc., and you can compute what is sigma. And then you can use exactly what I was saying. So then the nonlinear viscosity is defined as the stress divided basically the shear rate. So here the stress is sigma, which is this sigma here. And the shear rate is just, as I said, the time derivative of the source, because the source is the shear. Okay, so at the end of the day, after all this computation, what we discover is that our nonlinear viscosity is given by this weird expression here, divided by H0 prime. So you can check pretty easily that if you go to the linear regime, this definition, again, boils down to the standard definition of basically H3 divided H dot 0. The H0 dot, yes. So that's basically a simple checkup that you can do that you are doing things correctly. Now, okay, after this long introduction and this long discussion of the methods, we are ready to go to the results. So if you have any more questions about what we are actually doing and how we are actually doing, this is a good point to ask.
Can I ask, in the previous slide, I did not understand how do you calculate the sigma? What's the definition of sigma? Sorry.
Yeah, so sigma, let me write here. So sigma is the stress. So it's the XY ij component, if you want, of your stress tensor. And the stress tensor can be computed like with the standard holographic computation. So there is a standard holographic computation that allows you to compute the stress tensor of the boundary theory in terms of bulk data. And what we did here is exactly following that computation. The only caveat is that here that computation is a bit more complicated because our space-time is time dependent. So you have to be a bit more careful. So what you do is basically it's really the standard computation of the stress tensor.
I see. And probably this is the reason you said earlier that, here you will be in principle getting all possible derivatives, right? You are not restricting it to first derivatives.
No, I'm not restricting to first derivative. Indeed, here you see that I get I got up to 3 derivatives or 2 derivatives times 1. You see, this structure, it already tells you that it's fully nonlinear, the story. So this is, I'm not doing any approximation on the derivative, the time derivative to be small. So I'm keeping completely all order in time derivative, and I will do the full time evolution. And then we will see in which regimes actually things will simplify or not.
Okay, and simply to go to the hydrodynamic regime, you'll just throw away the higher derivative terms.
Exactly. So the hydrodynamic regime would be assuming that the derivative, the time derivative of H0 is infinitesimal.
Right.
And then I throw away all the terms. And I do the standard computation, and you will find the standard result, for example, 1/4 pi, if you want.
Okay, thank you.
No problem. Any other question? No. Okay, then let me go to the result. So first, the models. So these are the holographic models that we investigated. So we decided, of course, we were concerned with some kind of, universality structure. So we decided it was a good idea to consider more holographic models and not just one, to make some kind of more, robust statement. So there are 4 models here. 2 of them are extremely simple, and let me go through them one by one. So the first one is basically the standard Einstein-Hilbert action with a negative cosmological constant. For simplicity, we decided to stay in 4 bulk dimension. I will explain what this means, or we can discuss what are the limitations of this choice at the end, if you like. And so the background that we get, the standard background will be basically the Schwarzschild background, if you want. And the picture in the dual field theory is just having a conformal neutral relativistic fluid. So model 1 in the dual picture corresponds to having a relativistic fluid which is conformal and neutral. Model 2, we are just adding a Maxwell term, and this allows us to put some charge into this fluid. So this is basically now the same as model 1, but now our relativistic fluid is charged. Model 3 is something a bit more exotic. We add a term that basically allows us to dial basically the compressibility of the fluid. So I can give you more details at the end. For the moment, the important thing is that thanks to this term, I can basically decide how much compressibility I want to put in this fluid. And the last model is actually a model where we introduce a scalar field, and this scalar field was introduced to break conformal symmetry. So we choose these 4 models just to have a kind of large, plethora of different things, and to try to break all possible symmetries and things, and to see how much the results are robust in terms of these modifications. So, okay, we're ready to see a result. So this is a concrete example. So we run our time evolution, and we decide to put the shear rate for the moment to be constant in time. So I'm basically shearing this material with a shear which is increasing in time, and this gamma naught here determines basically my shear rate. Okay, so if gamma naught is large, this means that basically I'm far away from equilibrium, and the rate at which I'm deforming these things is becoming very large. Now, these specific plots here are for the model with charge. So it's a charged relativistic fluid, and therefore we define a dimensionless shear rate, which is basically gamma naught divided the square root of the charge density. And here you can see basically different plots. So these are time evolution. So on the x-axis, you will see the dimensionless time, which is basically gamma naught times t. And on the vertical axis, you see 3 different quantities. So this is the energy density, normalized by the initial energy density. This is the viscosity normalized by the initial viscosity, and this is the entropy normalized by the initial entropy. So what you find out is that basically you see when you go like at late time, so you start evolving your system, you will see that all quantities become strongly depending on the time. And there is some kind of power law behavior that you can understand analytically. I will show you later how. And all the quantity, of course, grows faster if I increase the shear rate. So you can see that the lowest curve, okay, is the lowest shear rate. So it's shear rate 0.3. So it's not exactly infinitesimal, but it's, let's say, it's not that far from equilibrium. And indeed, you see that all the quantities evolve very slowly with time. Right. On the contrary, we can increase the shear rate, and you will see that these quantities start changing very rapidly with time, and they grow very fast. So this is our setup. And one interesting thing of the setup is that we can control in a very precise way the energy dissipation that we do, that we produce during this shear. And the interesting thing is that we can derive a formula directly from the Einstein equation. So there is one Einstein equation, in particular the Einstein equation, which is a constraint, which is a non-dynamical, which basically enforces directly this kind of law that I wrote on the top. So this means that the energy dissipation is nothing else than the integral of time in time of the stress multiplied by the shear rate. So this is not something indeed extremely new. It's exactly what you expect in terms of power when you do a shear rate. So this coincides exactly with what viscoelasticity theory says. And we found pretty nice that actually the Einstein equation knows about that. So if you actually check the structure of the Einstein equation, one Einstein equation exactly tells you this. And we check numerically, and you can see that for different evolution, indeed, this formula, so these are this is the difference between the numerics and this formula, which is derived analytically, and you see that the difference is very small. So this is a very accurate check. And this is also a nice check, of course, of the numerics, because this formula is extracted analytically, and this is basically numeric check with the numerics. And this formula is valid all over. So you can go how much you want far from equilibrium, and that's what you will get. Now let's go to the most interesting result. So the first interesting result that we found is the following. So here you can see two things. You can see the energy density normalized by a power of the entropy, the correct power of entropy. And you can see the viscosity divided by the entropy. So this is time evolution, and this is for different shear rate. So you see the light blue is small shear rate, and the dark blue is basically very large shear rate. And what you see is that at the beginning, there is a period of time where this thing is completely non-universal. It's highly out of equilibrium, and the things are pushed away. But then after a while, at late time, even if the rate is still very large, you see that all curves asymptotes to reach a universal value. And this universal value, actually, you can see for eta over s is exactly the 1/4 pi that you expect. Okay. So then the kind of question is, okay, so this was kind of surprising for us because we were not expecting, let's say, this kind of non-linear time evolution to always go to the same value, or not even go into a constant. It was not clear why they should go to constant. We tried to explain this in terms of a universal attractor that is emerging. And indeed, we found an expression for the universal attractor. This is basically the structure that reproduce exactly the behavior that we see with the numeric. So here you can see that all these expressions are highly nonlinear, but then when you take the appropriate ratios, most of the things cancel, and you find again the standard, let's say, results. And also, for curiosity, we have checked basically how fast basically this attractor is reached in function of the shear rate. Remember, gamma naught, the biggest is gamma naught, the more you're out of equilibrium. And funnily enough, we saw that the more you're out of equilibrium, the fastest you reach this attractor, which is something, again, quite interesting. Now, one thing which is important to say is that, of course, we run these simulations for many different systems, all the systems that I was actually describing to you before. And as you can see, the results are quite robust. So, of course, the intermediate transient regime is very non-universal, and it depends a lot on, the type of deformation and the type of system. But then all the systems sooner or later go to this universal value. And notice also here, I want to also emphasize that we use not always the linear shear rate. We also put shear rate, which are completely different, like quadratic or square root or quartic, to try to analyze more situations. And that's basically the fact that the results are robust. But then we realized one thing, and we realized that maybe this is not so surprising. And the reason why it's not so surprising is the following, is that if you actually compute the ratio between there is a question?
Yeah, I have a question. So gamma is what? Gamma is gamma. What's the meaning of gamma?
What is the meaning of gamma?
Yeah, yeah.
Which gamma? This gamma here, the gamma on the x-axis.
Yeah.
Yeah. So that gamma in the x-axis is, let me go back. Is this one. So gamma is actually the shear deformation that we're doing. So gamma, and here for simplicity we took it linear. So basically the dimensionless time in this time evolution is not t, but is actually t times gamma 0. So large gamma means that you are at time much larger than this rate.
Okay. So this
small
is
gamma that you are. Yeah, that was basically the meaning.
Yeah.
And so yeah, I was saying, yeah. So then we thought about that, and actually I have to admit that the referees help us a lot in here. And so we were trying to understand what is the reason of this universality. And
excuse me, Matteo. So probably I misunderstood your message. So this, I thought you wanted to do the nonlinear regime, but so why? So you are still using the linear T gamma. So if we, I mean, this parameter.
No, so well, okay, so
only the initial value. I mean, in equilibrium regime, you want to use this linear behavior, and the non-equilibrium regime, you want to consider completely general gamma.
No, so the point is the following. So this gamma is the shear deformation, which for simplicity, we took, at least in some of the simulation, we took it linear. Okay. Yeah. So if you take it linear, then the gamma naught is the shear rate. Okay. So shear rate, if the shear rate is small, this means linear response. The gradient are small.
Okay.
So whenever gamma 0 is large, then you are far away from linear response and things becomes highly time dependent. And that's what you see in this plot. So if you see the light blue, you see things do not change much with time or very slowly.
Right.
You have to imagine as the x-axis is time in this plot. So you see that the light blue basically does not change fast in time. So if it doesn't change fast in time, it means the gradients are small and it means the linear response applied. But then, for example, for the blue curve, you see this change very brutal in time. So the gradients are very large. And this means that basically the hydrodynamics approximation that the gradients are small, it's completely gone.
Okay.
So this means that in this regime where gamma naught is big, basically the viscosity will depend on gamma naught. And I will show you actually how at the end.
Okay, I see.
So then we're okay here. So then, yeah, we were kind of, trying to understand why we saw that kind of universalities. And we realized one thing. We realized that actually, if you do a different normalization and you normalize your shear rate by the energy density, you find out that at late time, this value becomes quite small. And indeed, it follows a law, which is given by this 2 pi divided gamma. And you will see, so let's say that the complaint of the referee was that at the end of the day, even if the rate is large, it's not really large compared to the energy. So at the end of the day, when you are a large gamma, the energy wins over the shear rate. So effectively, you are in equilibrium. And I'm not sure I totally understand, and I agree with this, but I think it's a valid point. And therefore, what we thought was, okay, can we modify our setup in a way that gamma dot divided the energy density can be kept constant and large? And in this way, then we will be, without any doubt, far from equilibrium. So then, yes, of course, you can do it. You can basically use a kind of different setup, which is what I call here this magic shear rate. And you can see how the shear rate, the shear depends on time. So it's actually something that grows very fast with time. And now when I do this kind of deformation, my system will have a constant rate divided energy. So the light blue is basically doing a small deformations in function of energy, and the dark blue is actually doing a very fast one. And this is kept constant during the time evolution. So if this is large, there's no question that you are out of equilibrium, and you will be out of equilibrium forever, at late time and starting at initial times, etc. Another way to convince yourself that this is true is to do a different computation, which is actually what usually people do in far from equilibrium hydrodynamics, is instead of consider our stress tensor, which is off diagonal, you can consider the pressure anisotropy. So you can basically, at least in our setup, you can diagonalize this matrix, and you can find out basically the difference between the pressure in the two directions, normalized by the sum. And it turns out that this quantity is actually just the value of sigma divided p, which makes a lot of sense, because basically what it's saying is that if you are far away from equilibrium, basically, remember the equilibrium fluid is isotropic, so there is no off diagonal. So this is basically another way to say that if the off diagonal becomes as large as the pressure, as the diagonal, then definitely you are far away from your initial equilibrium configuration. And indeed, what we find out is that if you do this kind of computation with our setup before, you find this blue curve. And indeed, the referee was right, that the value of the sigma divided p for that simulation becomes reasonably small. So it's not clear from our numerics, we cannot push it more than that because it's very challenging, but it's likely that it will become small or even goes to zero. But now you can see the new setup. So the new setup is completely different, because as you can see, sigma divided p goes to a constant at late time, and this constant is actually huge. So this means that basically the time evolution done with this magic shear is definitely completely far from equilibrium, and there is no effective equilibrium of universal attractor or anything like that. And in order to verify also this better, we plotted this sigma divided p in function of the normalized shear rate. And you can see that indeed the higher the shear rate, so this is a measure of out of equilibrium, the higher this sigma divided p. And when this value, sigma divided p, you see at the beginning is more or less linear. Actually, you almost follow a linear law. You see one is here. And then it deviates. But definitely, when this confirms that when we take this constant, and remember now this will be a constant over the time evolution, large, then you will be obviously far from equilibrium. One thing that we found, which is interesting, is that it looks like there is some kind of saturation here. But unfortunately, we weren't able with the numerics to establish it's really a saturation. This will be interesting because this will tell you that there is basically a kind of upper bound on how much you can go far from equilibrium. So this will be very interesting because you see, you can push your rate as large as you want, but basically the system at a certain point will not go beyond a certain value of far from equilibrium, if you like. And so we redid the simulations with these values, this setup, and now we are totally out of equilibrium, and that's what we found. So what we found is that indeed there are two features here. So the first feature is that still, even if we are completely far from equilibrium now, and notice this is also valid for non-conformal systems, you find that this eta over S ratio approaches a constant at late time. So at late time, you are completely out of equilibrium. So this is basically the rates are enormous compared to the energy density, but still eta over S is nicely and constant. And but you see that the value decreases with the shear rate. And this is basically what you see. So if you plot the value of eta over S when it approaches a constant in function of how far from equilibrium you are, you find that actually close to equilibrium, you find the typical 1/4 pi value. So this is the computation that you will do basically with standard Kubo formula techniques. But then when you go far from equilibrium, this eta over S value is still constant in time. So there's no time dependence. You reach a state with constant eta over S, but the value drops down, and it drops down pretty fast. And when you are extremely far from equilibrium, it almost reaches zero. So this is kind of interesting, and it's actually we find out that it's consistent with some previous results that Romanchke found in some Bjorken flow. And I guess it's interesting to understand first of all, if there are physical consequences of these things, and then second, what is really the meaning of this. So it looks like that the eta over S ratio, making this in this strongly coupled relativistic fluid, becomes very small if you push this fluid from equilibrium. At least we're using this definition. So let me conclude almost in time. So what we found? So we found that there is still some universalities in the sense that I described before. And in the case of effective equilibrium, so whenever this shear rate is large, but it's not that large compared to the energy density, we have found this emergent universal attractor, which looks like that you are kind of reaching some state, which is kind of a steady state. And on the contrary, we found that if you really push this system far from equilibrium and the rate is much larger also of the energy density, then the value of the eta over S ratio is actually parametrically smaller than the equilibrium value. And it's a very valuable question, I think, to understand, first of all, if there are setups like where this can happen. And second, if you can kind of see this feature, like, you know, if you can really do an experiment and see that with the shear rate, this can go down. As I show you, of course, in a standard fluid that you can put in a container, you can do that. It's less obvious if you can take, you know, a droplet of coagulum plasma and put it in the container. That is a more complicated things. And I'm not an expert in, you know, in nuclear physics, but my hope is that at a certain point we will be able to at least check these kind of predictions with, you know, in the coagulum plasma, making some nonlinear shear analysis. And just some more general questions for you, which are related to this to our founding. So, so first of all, regarding the first part, where we still find this kind of universality, is it really hydrodynamics working better than it should? And here I want actually to make a comment, which is something that I learned recently from a collaborator, and I think it's very interesting. So as you know, hydrodynamics is not a convergent series. But I learned something which is actually standard knowledge in mathematics, that if your series is not convergent, it actually, if you cut it at lowest order, it gives a much better approximation than a convergent series. Because a convergent series it's slower in the first order. A non-convergent series is actually exponential between reaching a minimum, and then it goes up. So if you cut a series at, say, order 2, 3, or 4, a non-convergent series will do a much better work than a convergent series, which is something very interesting in particular, thinking of all these examples where we know that hydrodynamics seems to work better than it should. Now, of course, the other question is, can we find more examples of this sort where, you know, there are these universal features appear far from equilibrium? Are they really universal? What they really mean? And this also is connected with emergent behavior far from equilibriums, order far from equilibrium, or instabilities, etc. And then in general, I think it's a very interesting question to start to explore nonlinear response in a strongly coupled system, including holographic models. So far, most of our analyses have been focused on linear response. You can imagine electric conductivity, shear viscosity, thermal conductivity, all these things. But of course, you know, in the lab, we can do much more than that. And maybe, you know, certain features of these systems, which are different from the standard one, are hidden in the nonlinear response rather than the linear response. And another thing that it would be very interesting is to try to see if there are relations between the nonlinear response and the linear response. And just with these questions, I end up here, and I want to thank all of you for listening, and once again, APCTP for organizing this nice event. Thanks.
Okay, thank Matteo for the nice talk. So now the session is open to question and comments. Any question?
Can I ask one question?
Yeah, sure.
Yeah. So you said that, you know, there is something like this effective equilibrium that is emerging, right? Which is still far from equilibrium, but looks like equilibrium, right? So suppose I do a expansion around that equilibrium, would the things be, would the hydrodynamic expansion will hold near that effective equilibrium, away from actual equilibrium?
That's a very good question. So that's something actually that we are trying to do now, to try to see if adding higher orders or resumming the hydrodynamic series, we will get the behavior over there. So if you stay exactly at equilibrium, this universal attractor will basically explain very well what you see. I'm not sure about perturbation. So it's not obvious to me how to go over there and do small perturbation on top of that state. It's something quite challenging. But definitely, you know, one thing to think is exactly on the line of what you're saying. You know your hydrodynamic expansion can you resum it? Can you do something in a way that the original hydrodynamic series knows about that? And I would say that, you know, there is hope that this is happening. And as you know, there are many other results in terms of these attractor, trans series, resum hydrodynamics, etc., that seems to indicate something like that.
Right.
So I think there is hope. I think it's a very interesting question, and I don't have an answer right now, but I think it's a interesting avenue to be explored.
Just to add a comment to that question, you know, it is very well understood that rather than looking at the full hydrodynamic evolution, if you look at, not in the case that you are looking into, but let's say you are looking into linear regime, and if you look at equilibrium and around equilibrium, then all the known hydrodynamic constraint, you know, comes out of that. You don't need to look at the full evolution. Like, for example, shear viscosity has to be positive, or there are some equality type relation. Those things come out. So I was just wondering, and you know, at equilibrium, you can also write down effective theory, which describes the fluid dynamics. So I was just wondering if you can write down an similar effective theory at your pseudo equilibrium, or you know, effective equilibrium, and doing an effectively perturbation, you would also be able to generate certain interesting bounds on your transfer coefficients. Anyway. Yeah,
I think that's a good question. Do you have in mind something like Keldy-Schwinger formalism, or like this kind of effective field theory for hydrodynamics, or?
Yeah, more like the equilibrium effective hydrodynamics, where you write down in terms of background fields, what are the possible terms that are allowed, and then, you know, do perturbation around them to find out other terms, which are not really equilibrium quantities.
Yeah. So for me, the main question there, sorry, go ahead. So yeah, the main question for me is that definitely that kind of state at the end doesn't look like thermal equilibrium. So it's not obvious which kind of constraint I have to put on that.
Right.
And I agree with you that maybe taking the effective field theory of hydrodynamics and relaxing some constraint, you can probably describe also that state over there. Yeah.
Okay. Thank you.
But we didn't do anything in that direction. It's something that we were thinking, and but I cannot say anything like meaningful at this moment.
Okay, thank you.
Okay, so I guess Shanhui had a question.
Yeah, I have a question. Do you consider the disorder, the effect of disorder?
You mean spatial disorder or time disorder?
Yeah, spatial and time. Yeah.
No, we didn't do anything like that. I mean, the numerics are already quite complicated without any disorder. So we didn't think about that. I mean, in principle, you can definitely drive these systems, adding some kind of disorder on top of the time perturbation. And I honestly have no idea what that would do to our results. But it's definitely something that one could do. So one could possibly put some kind of random perturbation in time and trying to see what happened. And in principle, one can also put some random perturbation in space, but I don't see much the motivation to do that, in the sense that now you want to consider some kind of randomly disordered fluid, or I'm not sure what would be the idea. Also, take into account that if you also break translation in space, then the definition of viscosity becomes even more complicated, and I don't even know how to define a viscosity, because then you are not only time dependent, you will be also spatial dependent, and then things become highly complicated. I would say that adding some disorder in time, like some random noise, should be doable, and it might be interesting. Adding disorder in space, I think it's terribly hard, and I don't see a strong motivation to do that.
Okay.
So any other question, comment?
I have a simple technical question. So when you solve the nonlinear differential equation you showed, which boundary condition should we impose to solve them?
Mm-hmm. Yeah, well, let me see. I'm not sure I have it, but yeah, I mean, I only have it for this guy here. So the boundary condition here is basically, so let me see if I can write on it. Yes, I think I can. So this is the source related to this operator. Okay, so this operator, you see, modulo the sinh is basically hxy. Okay, so this operator couples to txy. So this means that this h0 is basically a source for hxy. And what you want to put here is you want to put an h0, which depends on t, because you want to do a shear rate. So if you put h0, so h0 that depends on t. So if you put it like exponential of e to the I omega t, that is basically what you will do in linear response. So it's the same boundary condition that you do in linear response when you compute, let's say, the viscosity. Now, the boundary condition that we put here is basically this h0t corresponds to our shear rate. Sorry, to our shear deformation. So this is basically the definition, because this is, you see, this is the source associated to txy. So basically, a leading order, right? If you are in linear response, you will have the txy is equal to eta times hxy dot. Right? This is the standard story. Now, hxy dot is actually this guy here, dot. Now, and so basically that's the boundary condition that we want to add, because we want to add this source. So we want to shear our system. So the boundary condition is we put a non-trivial h0 t, which is gamma t. Now we do different simulations. So the simplest one that I show you, gamma t, is basically just linear in time.
Okay.
And then of course also this is not necessary. Of course, you can decide to put whatever. The important thing is that the time derivative is non-zero, so you have a rate. And also for numerical reason, there are more details in the system, but you cannot just start like this. So you have to introduce actually this deformation in a smooth way. Otherwise, the time evolution is singular at the beginning and you have trouble. So we introduce basically a function that moves this. So if you see really in the paper, so the gamma in function of t is not exactly linear like this, it's smooth a bit and then linear. So this is why the initial regime is actually, we cut it out because it's non-universal. It's just given by this initiation function. So that's basically the setup. So the boundary condition that we put is just that.
Okay.
And one thing, let me say also one thing. So in principle, there is another source here that you can choose to put or not. What is the meaning of this source? So this source is related to change in volume, because you see it's in front of everybody. If you compute the volume in the XY direction, this actually is related to that. So this would be related not to a shear, but to actually to a deformation, which is a volume deformation, like pressing or pulling this liquid. And if you compute the response to that guy, you will find actually other quantities like bulk viscosity, for example. So for example, one thing that we want to check is with this guy, you can compute now the bulk viscosity. As you know, the bulk viscosity in a conformal system is 0, so there's not much to see. But if you are non-conformal, like in the last example that I show you, also the bulk viscosity is there. And with a similar formula, one can basically compute this bulk viscosity, and one could see also if the bulk viscosity is, has some features or not. Did I answer you, Andrew?
Yeah. Oh, thank you.
Sachin has another question.
Yeah, I'm just curious about, so, if I try to use this way and then run through this model of fluid gravity correspondence, where I try to systematically find out stress tensor, zeroth order, first order using the gravity, is that possible to do in the sense that, the way one can try to derive the stress tensor, would that be possible to do systematically?
Yeah, I'm not expert in the fluid gravity, but my understanding is there you are doing also gradient expansion, right? Because you're doing basically the hydrodynamics expansion.
Yeah.
So I'm not sure.
There you go to, yeah, that's right.
So I'm not sure. One thing that you can do, and I think people do it, you can go all order in the fluid gravity. And so then basically you can go much beyond the linearized hydrodynamic expansion. But I doubt that you will get analytical results. I don't know.
Right.
So
No,
if you don't
sometimes
get
what happens is
analytical,
right, please.
no, just that if with this all order fluid gravity correspondence, you don't get analytical results, then I'm not very sure what you gain. If you can somehow resum or write this in kind of a series or whatever, then I think it would be very interesting. Yes, definitely.
Right. Sometimes what happens is that in the non-linear region, you break this derivative expansion, of course, and also you get some very interesting scalings, right? 1/3, 2/3, that kind of scaling. I was just wondering, is there in your way of thinking, would that be possibility of getting those kind of non-trivial scaling or not? I'm just curious about this one.
Yeah, we thought about that. I mean, actually, that is the way that kind of people are trying to derive this attractor out of equilibrium attractor, right? All this like power of 2/3, like in Bjork and flow and things like that.
Yeah.
Should come. My understanding, which is very little, is that they should come from resumming somehow the hydrodynamic series, right? These are kind of non-perturbative effects that come when you resum everything. I'm not sure, I'm not aware if you can get anything like that in fluid gravity, but if you have some reference about that, please send to me. I mean, it's interesting.
Okay, thank you.
Thanks to you.
Okay, so final question. Is there any more question? Okay, so if not, let's finish today's session. Let's thank Matteo again. And I would like to thank everyone in this Zoom session.